Um, and then this time we have that 10,000 Newton force. That vector is 70, 71, 70, 71. And then we have the internal loads. So add those up, set it equal to 0. So this is what I got for tension. Anybody disagree with that? And then for shear force, I got the same linear coefficient, but then a different constant. And then for the rotational equation, we have a contribution from the y component of the distributed load. That's going to produce a clockwise moment, so I got 3468 over 2 x squared. Then we have a positive moment produced by the y component of the, this 70, 71. Then we have plus m minus vx is equal to 0. Rearrange it. You get 1734x squared minus 3468x squared. That's from the vx. This one. What's going on here? Oh, no, that's right. So 1359 times x, and then 7071 times 0.7071 is minus 5,000. I mean, that's positive 5,000. Move it to the other side, we get the negative 5,000. So this is what I get for the moment equation. Anyone else get that equation? Okay. And so if you plot those out, it's a little tedious to figure this all out by hand. It's easy to do in Excel. Or MATLAB, but Excel's probably the easiest, Just put all your x values in one column. Next to it, use the function up to the right point, use the next function up to the right point, and it does it right for you. That's what I would recommend. But I got this for my tension, this for the shear force, and then I'm a little perplexed about the bending moment because I seem to be getting.
Does it start at negative 5,000?
The bending moment?
Yeah, when x is 0.
Well, x isn't equal to 0 because this is only good for x from 0.7071 to 1.4.
Yeah.
Okay. So what we should get just by thinking physically about it, we don't have any couples at either endpoint, right? They're both pin joints. So we should have it starting and ending at 0 and meeting at a cusp. But I don't seem to be getting that. But let's pretend I did for now. Anyone have any questions about that? Okay, so let's figure out where all of these three members have their maximum bending moment, tension, and shear force. So the candidates are this 10,000 Newton shear force, this 5,900 Newton tension, or 5,900 Newton compression down here, and this. And from the other ones, what did we get? A tension of, or a compression actually, of 10.9 newtons. That's bigger than this one. And what's the one we didn't do today? We didn't do the. Okay, so that one has about the same shear force, smaller bending moment, smaller tension. So So what I'm trying to say is this is the maximum tension compression. It happens in that vertical member. And the maximum shear force and bending moment are here and here. And how do these look different in general than when we did this problem with no weight to the members? They, yeah, do you have those up there from last time when we did them? I mean, the first time?
The maximum bending moment was 5,000 on number 2.
Mm-hmm.
The maximum shear force was 10,000 on number 2. And the maximum tension moment was
Mm-hmm.
number 1 at 5,000.
So the main thing you get is, I mean, just looking qualitatively at the curves, is in that vertical member, you get sloped graphs to your tension compression diagram. When you treat gravity, you got horizontal sections when you didn't treat gravity. In that diagonal member and in the horizontal member, actually, you got sloped tension and shear force graphs as opposed to horizontal. And for the bending moment, you got quadratic sections instead of linear sections. Okay, so that's just what you get in general when you add distributed loads as opposed to only point loads. All right, anybody have any questions about that? I posted some new practice problems. I posted a set on just general internal loads, and then I posted 2 problems where you have to do internal loads for structures with weights. Okay, so you're just going to use the same method. Oh, we don't have class on Thursday. We don't have school. Yeah, Veterans Day. Yeah. Some of the presidents were veterans, though, so there's some overlap. And so today I'm going to get up your next problem set. Okay, I'm almost done with it. So look for that, and it'll be due a week from today. Okay, and a week from today, our next class, we'll start working on friction, the next topic. Okay.